So following with the session, now it's time to analyze batch normalization. Batch normalization is a new layer introduced quite recently. I think it was in ICCB this year. The paper has been in the archive like for a couple of months already, like 3 or 4 months. The idea is quite simple. Before batch normalization, a similar layer was proposed by LeCun a couple of years ago. The idea is to take your mini batch, basically to compute a mean and a standard deviation of that mini batch, and to normalize each of the images by subtracting the mean and dividing them by the standard deviation. And then with that sort of whitened mini batch, over the top you apply like a shift and a scaling factor that you learned, and you learn one shift and one scale per each of the features, per each of the layers. Sorry, per each of the feature maps. So what this operation is trying to do is to create is to make the data always have covariance 1, unitary covariance. This is important because the deeper you go through your net, since we have all these range of nonlinearities, the more unstable your signal gets. So the deeper you go, the easier it is to find your signal becoming zero or exploding, and the same for your gradient. So what batch normalization is trying to do is to get everything under control, making the gradient like sort of unitary. And that's quite nice because that helps to do deeper nets. That speeds up the whole process of training, and it has really beneficial properties. So I was gonna see batch normalization for AlexNet in CIFAR10. So this is the basic AlexNet we have seen in past session. We're gonna run it in the reduced CIFAR10 version. We're gonna be using this again as a reference. We have chosen Xavier's initialization in this case, but you can also try with Hess, or even the standard Gaussian initialization from the original AlexNet. This is gonna take a bit longer than the previous examples in MNIST, but it can be still done. So I'm gonna stop the video and we'll be back with you in a couple of epochs. Okay, the process is about to reach 20 epochs. We're gonna stop it here once it has completed the epoch number 20. You see that, yeah, things are gonna be weird. We have several peaks. We have several going up and down. So that is telling us that well, this terrain is getting a bit harder than what we saw before in MNIST using LANET. Yeah, this terrain is way harder. So turning AlexNet in CFAR10. So for the classification error, we got around 65% of error for training, 75 in validation. So not too good, actually. And it was sort of expected. So when you start training like deeper networks, standard initialization is not enough. You need to complement that with clever ways of regularizing gradients and the input signal. So let's gonna see now what happened when we use batch normalization. So following with the script of the session, we are now gonna see AlexNet train bnorm, which is a version of AlexNet in which we have included several batch normalization layers. So in batch normalization, we only have to indicate like the number of feature maps. So for example, if we set a batch normalization layer at the beginning of the net, so that's gonna be like receiving the input images that has 3 channels. So yeah, we need to indicate that the number of channels is 3. And then we're gonna set up a batch normalization layer after each ReLU. Okay, so we have one after ReLU 1 with 96 channels, so matching the number of output channels of the last convolution. We have one after ReLU 2, again matching the number of output channels. And the same for ReLU 3, 4, 5, and 6. And we stop here. You could also add it to the ReLU 7, but in this case, just for simplicity, I haven't done it. So the parameters of the batch normalization are 3. So three sets of parameters. So we have like the scaling factors, 1 per channel, so in this case 3. The shift or the biases, again 1 per channel, and then we have like the momentums. Before in the previous video I say that batch normalization is computing an average and a standard deviation per mini batch, and that's usually the case. That's usually the case, and it's true in general. But in this implementation, what MatConvNet does is instead of computing the average and the covariance per each of the batches and use that, is sort of learning those parameters. Is learning both the mu, so the mean, and the standard deviation for all the batches, instead of using 1 per batch. This is especially good for validation, because in that way you don't have to recompute mu and sigma for the whole dataset. So that's usually the problem with batch normalization. So this is a beneficial point of MatConvNet with respect to other implementation like the one in Cafe. Okay, let's gonna have a look to what happened when we run this code. Okay, as a reference, we will keep previous training. So we see how the both objective and error for train are decreasing, which is a good good thing to see. And for the first epoch, our train error is already much lower than it was in the original net. So 82% of error against almost 90% of error. Let's wait for the second epoch to compare. Yeah, and it moved all the way down to 74%. Batch normalization is using the momentum, it's learning the momentum, so it's learning the statistics for the average and the covariance of each of the channels. At the beginning, using batch normalization is gonna produce like having like a lot of going ups and downs until it sort of start learning a proper mu and sigma. So, but still, don't worry much about it, because after a couple of epochs, sort of get solved and things start going very well. So don't worry if you see like going up and down during this training. It's just because of this implementation of batch normalization with. See you back after a couple of epochs. In epochs we so which is better than what we got before, what was around 75. So batch the way it managed gradient is unitary, so it's producing better results in less gradients data. That's an important concept, because there are several papers are trying similar things in ways, but like idea, like regularize your gradients, regularize your data, so you improve gradients and reach better results in less time. Okay, some overfitting. This is true in general, and it can be improved by reducing the size of the mini batch. So although it's helping to reach in this case will mean something like 10 or 15 images. Um, to the last point of the session, like trying to place batch normalization before ReLU layers, because in this experiment, if you remember, we have put them like after ReLUs. And in my experience, and this also has been reported by other people, putting batch normalization after helped a lot to improve convergence. But originally, batch normalization was proposed to be before the nonlinearity, so just after the convolution. So I'm also leaving you the task to place batch normalization for the nonlinearities, but see what happens to the convergence of the method. And also try to experiment a little bit changing the batch size, as I said before, to check that actually helps to reduce the overfitting. Okay, that is it. This is everything, all the basic and standard tricks people use to improve convergence and to help the training procedure. Okay, hope you enjoy.